morning. So section 2.1 is really a very simple section. It's on matrix operations, adding matrices, multiplying matrices, and a lot of it is common sense, I would say. They have always before the like when a chapter begins, at the beginning of the chapter, they always show like a application where matrices are used. And this example is about computer models in aircraft design. And they, hold on here, let me get that off there. They talk about like how, for instance, this application, this aircraft design application, if you're solving a system of linear equations, it may involve up to 2 million equations and variables. So that's a pretty big system, and that's why we need computer software like MATLAB to handle things like that. Because systems are system of equations. You can have massive systems of equations, and I don't even know if MATLAB could handle that. But I mean, I haven't tried it, but you would need definitely some kind of computer software. And that's why one reason you're getting acquainted with computer software. So, all right, and then, you might want to read that introduction if it interests you. So in section 2.1, chapter 2, our ability to analyze and solve equations, systems of equations, will be greatly enhanced when we can perform algebraic operations with matrices. So, let me see here. They talk about representing a matrix A this way. If you have the columns of a matrix A denoted by A1 up through AN, the matrix A can be expressed as in this notation where they denote the column vectors of the matrix A. They mention about a diagonal matrix. A diagonal matrix would be a square matrix, an n by n square matrix, whose non-diagonal entries are 0. So, for instance, the identity matrix is an example of a square of a diagonal matrix. If you think about the identity matrix, how's an identity matrix defined? Well, let me just show you real quick here. I think you might have seen this in homework, but like, for instance, if you were to have the I2 identity matrix, that would be equal to 1, 0, 0, 1. And that's a type of diagonal matrix, an identity matrix. All right, let's continue on here. So let me make sure you're seeing what I'm seeing. Okay, very good. One moment, class, one moment. Okay, so the book shows basically here's like a regular matrix, okay, where they denote elements of the matrix. So like, for instance, in the top left-hand corner, the A11, why is it called A sub 11? Well, that's because that is the first, that number that goes there in A11 is in the first row in the first column. Okay, first row in the first column. So actually, let me so this is in the first row in the first column of the matrix. Okay, and if this matrix has m rows, that value there is in the mth row in the first column of the matrix. Okay, if you're in the if you have an element in the ith row in the jth column of the matrix, that would be A sub ij. So that's just how a matrix is denoted. No big deal. Are there any questions so far? Okay. All right. Well, then let's continue on here. So now we talk about sums and sums of matrices, okay, and scalar multiples of matrices. So, like for instance, in example 1 here, you have a matrix A and a matrix B and a matrix C. And the matrix A and the matrix B have 2 rows and 3 columns. So that allows you to add those 2 matrices. If the 2 matrices are the same size, you can add those matrices. And when they add A plus B, I notice they get a 5 here. They get a 5 there in that spot. Well, how are they getting a 5 there? How are they getting a 5? Who can chat that out? How they get that? That's right, Olivia. That's right, Natalie. 4 plus 1. Yeah. So it's intuitive that if we're going to add 2 matrices, if we can add them, we would add them element by element. So 4 and 1 make 5. Okay. Let's look at this number 9 here. Well, 9 is in the second row, third column. So if we take the 2 and the 7, which are in the second rows, third columns of A and B, we add them and we get 9. Okay. Are there any questions on this? Okay. Well, they note here that A plus C is not defined because A and C are different sizes. So the matrix C is a 2 by 2 matrix. The matrix A is a 2 by 3 matrix, 2 rows, 3 columns. So you cannot add matrices of different sizes. Okay, you can multiply matrices sometimes of different sizes, but you can't add them or subtract them. Okay, now they also talk about a scalar multiple of a matrix A. Again, this is intuitive. So here, if you take that matrix B that you had in example 1, and you go 2 times B, well, all you do is you multiply every element of the matrix B by 2. Okay, so now you know how to multiply a scalar by a matrix. And then, of course, you can take the difference between a matrix A and 2 times the matrix B. I mean, you can just do the allowed arithmetic, and everything follows nicely. So this is very intuitive. And in theorem 1 here, they give properties of matrices that are allowed, and it's you know, pretty common, pretty intuitive, the properties. Okay, so are there any questions on that? Okay. All right, then let us proceed on here. So next thing we want to talk about is matrix multiplication. Okay, so they have a little note here that if you take a matrix B and multiply it by a vector x, it's going to transform the vector x into the vector b times x. Okay, that makes sense because the matrix B times a vector x is a new vector. Okay, but then you can take that vector and multiply it by matrix A. And then you'll get a resulting vector A times B times x. And you can write A times the vector B times x as the matrix A times B times the vector X. Okay, you're still preserving the order, and sometimes it's useful to look at matrix that kind of multiplication that way. So I just wanted to demonstrate that in figure 3. It's not, well, here actually. So not a big deal. I think this is pretty intuitive. I want to get to this definition here. Now this is something that's interesting. Okay, if A is an n by n matrix and B is an n by p matrix, okay, and B has column vectors, B1, B2 up to BP, those vectors, then the matrix product A times B, okay, can be represented as A times the matrix B, where you write the matrix B as the column vectors of B, and then that will equal the matrix whose columns are given as A times vector B1, A times vector B2, and so forth. Now that's an interesting result. And what I'd like to do is show you intuitively why that's true. So what I'm going to do here, I want to bring up the hold on here. I want to bring up an example here. Yeah. Let me bring up this example here. For matrix operations. Okay, and let me give you a moment to copy this example down. And I should say show, hold on here, it should be show 2 ways. Show 2 ways to find the product A times B. All right. Okay, so, all right. So what I'm going to do here, first of all, when we look at this, what are the dimensions of the matrix A? In other words, how many rows, how many columns on matrix A? Good, Catherine. That's a 2 by 2 matrix. And what about the matrix B? What are the dimensions? Good, Nafani, Benjamin, Catherine, and Olivia. It's a 2 by 3. So to help you understand that definition that you just saw, I want to do the matrix multiplication the old-fashioned way that you're used to. But first, we always have to ask, can these two matrices be multiplied? Is matrix multiplication defined between the matrices? Now we know the matrices can't be added together because the matrices are of different size. But can these matrices be multiplied together? They can. They can. That's right, Nafandi. That's right, Marvelous. The column number of the first matrix matches the row number of the second matrix. They match. They match. So what would the dimensions be then of the product matrix? How many rows, how many columns would the product matrix have, AB? Good, Abby. Good, Lewis. It's a 2 by 3. Absolutely right. Because 2 by 3. You look at the outer values to give you the dimensions of the product matrix. Okay. Are there any questions on that? Okay, then let's get to our solution here. We want to show two ways to find this product, A times B. So the first way is the method. It's actually listed second in the textbook, but it's the row column rule. And this is the one that certainly many of you have seen. What you do is, well, let me give you a moment to copy this down. Okay, let me give you a moment to copy that down, and then we can talk about that. Okay, so why do they call this rule the row column rule? Well, look at what we do here. So how do we get this entry here? This entry is in the first row and the first column of this product matrix, A times B. To get that entry then, we had to multiply the first row of matrix A times the first column of matrix B. And you do it element by element. So 2 times 4 plus 3 times 1. Let's look at this element here in the matrix. That element is in the second row, first column. So to get that element, you take the second row and multiply it by the first column. All right, are there any questions on that? This element's in the second row, first column, so you have to take the second row of the matrix A and multiply it by the first column of the matrix B. Let's do one more. Let's do one more. Let's talk about let's see, this right here. That entry is in the second row and the second column. So to get that entry in the product matrix, you have to take the second row of matrix A and multiply by the second column of matrix B. And that's why they call this the row column rule. And so you can get the other values similarly. If you let's pick one more here. Let's say you wanted to know how we got this entry here. Maybe I'll put it in red. Red shows up a little better. This entry is in what row, what column? This entry is in what row, what column? Good. Row 1, column 3. Good, Eleanor. Good, Benjamin. So if we take row 1 and multiply that by column 3, 2 times 6 plus 3 times 3, you get that entry. Okay? And are there any questions on how we use the row column rule to multiply two matrices? How many have seen that maybe in a previous class? That's usually what's taught in other classes. How many have seen that before? Done that before? Okay, all right, a number of you. Great, excellent, excellent, excellent. Okay, well that's one way, that's a common way to multiply two matrices. The second way is this definition. Okay, this definition, and I think I have to spell that better. Right, definition. The definition is the one that we looked at on just before example 3 in section 2.1. If you have a matrix A and a matrix B, and the matrix B consists of these column vectors, B1, B2, and B3, you can find the product matrix A times B this way. Every column vector, well, the first column vector of A times B is A times B1. The second column vector of the matrix product A times B is A times the vector B2. And then A times the vector B3 is the third column of the matrix product. So it's a very elegant way of looking at matrix multiplication, and it's very handy for theoretical purposes to understand matrix multiplication that way. But I think you should understand why it's true. Okay, so what I do, let's show this. Let's show this. So what I do is I have the matrix A times the matrix B. Okay, and I denote above the matrix B the column vectors. So these are your three column vectors, B1, B2, and B3. Now what I do is I first do the row column rule to multiply the two matrices, because you agree you're comfortable with that. And from that, I'm going to show you why that definition works. Okay. So let me give you a moment to catch up here. Let me know if you have any questions. Okay, so now let's look at each of the columns separately. Let's look at this first column here. Do you agree that that first column, which consists of elements 2 times 4 plus 3 times 1, and the elements 2 times 4 plus 3 times 1, and 1 times 4 plus negative 5 times 1, do you agree that that's the same as A times the vector B1? Here's B1 right here. All right. Benjamin's comfortable with that. Nafani's comfortable with that. Catherine's comfortable with that. Thank you. Excellent. All right. Is anybody not comfortable with that? Is anybody uncomfortable? Let me know. Okay. Well, then let's go to the second column. The second column, if you think about the row column rule for that, that second column would be the same as taking the matrix A and multiplying it by the vector B2. And similarly, the third column, okay, is the same as taking the matrix A and multiplying by the vector B3. Okay, and you have the vectors up here, they're defined there. Olivia, there's no difference practically in the multiplication. It's just understanding it, a different way to understand it theoretically. It's going to be handy at times to understand matrix multiplication this way. Sure, no problem, no problem. So what happens then is you'll see that, you know, I mean, this then, the A times B, you know, we took matrix A times matrix B, and we showed matrix A times matrix B is equal to, we can represent that matrix product as this matrix here with these 3 column vectors. And you can actually represent that also as the matrix A times the matrix B. You can write it like this because we can distribute, right? Well, I want to be a little careful here. Got to be a little bit careful here. We can distribute. Matrix multiplication is distributive. Okay, matrix multiplication is distributive. That's hold on here. Yeah, that's one of the properties of matrix multiplication. So you see matrix A times matrix B, B1, I should, matrix A times vector B1, matrix A times vector B2, and matrix A times vector B3. Okay, and are there any questions on that? All right, well, if you're good with that, I'll go back to the textbook. I want to continue my guided tour of section 2.1. Does everybody have the example copy down okay? Where we can move on? Okay, one moment here. Hold on here. Sorry, one moment, class. I'm trying to bring up the chat thing here. I heard a chat, but I can't see it for somebody. Can't see it. Hold on. Okay, great. Man, hold on. What's that? Hold on. Okay. All right. Nafani's good. And all right, so let's move on here. So back to the book. Back to the book. So now the definition here of matrix multiplication should be, you should have an intuitive feel for that definition. Okay, and then they give an example where they compute the matrix A times B, and that reinforces what we just did. That example 3. And these are just some things that we've talked about, just kind of moving through here, moving through. Properties of matrix multiplication. These are some key properties here in Theorem 2 of matrix multiplication. We actually used one of them. We used this one here. A times B plus C equals A times B plus A times C. Matrix multiplication is distributive. Also, if you take a scalar, times a matrix product, hold on here, if you take a scalar R times a matrix product A times B, that's the same as R times A times R times A times B, or A times R times B for any scalar R, and that's useful at times. Also, the identity. If you have an identity matrix times A, that'll equal A. And that'll also equal A times the identity matrix. Okay, so that's why they call that matrix I, that diagonal matrix I, that just have ones down the diagonal. That's why they call that an identity matrix, because I times A equals A times I. Okay, are there any questions so far? Okay, whoops, hold on. I did the thing I usually do. Okay, something interesting. Let me ask, do you think, if you were to ask somebody, does A times B equal B times A? In other words, if you were to ask somebody, let's say you have two matrices, A and B, and they're defined so you can multiply them. Do you think A times B equals B times A? Okay, Abby doesn't think so. I mean, if we have scalars, we know like 2 times 3 equals 3 times 2. So for scalars, hey, we have no problem with that. But for matrices, is this true in general? Is this true in general? Well, Abby and Lewis are right. The answer is no. Matrix multiplication is not commutative. It is not commutative. Okay. Hold on. So why, we can just see an example of that. Let me bring up an example here. So in example 7, they have a matrix A and a matrix B, and they multiply A times B, and they multiply B times A, and they get two two different product matrices. These two matrices are different. So, you know, to disprove something, all you need to do is find one counterexample. And that's a counterexample. So in general, A times B is not equal to B times A. Okay? Also, because of that, if you have A times B equal to A times C, it's not true in general that B equals C. It's not, well, I want to be careful. That doesn't really, that's a different thing. But because of the way you multiply matrices, you could have a product A times B equal to a product A times C, but B is not equal to C. That can happen. All right. And also, if you have A times B and it equals the zero matrix, meaning a matrix where you have all zeros, it doesn't mean that A equals 0 or B equals 0. It doesn't mean that. Now, you're used to that with numbers, but it doesn't mean that with matrices. So these are just some rules, some things you should be aware of. Are there any questions on that before I move on? Okay. All right. Well, then let us move on here. Let us move on. So powers of a matrix. Powers of a matrix. Whoops. Hold on. Yeah. If you have, okay, if you have A to the kth power, okay, and we're assuming A is a square matrix. A square matrix means it's an n by n matrix. Same number of rows, same number of columns. If you take that matrix A and raise it to the kth power, that just means taking A and multiplying it by itself k times. And if you have A to the 0th power, that's interpreted as the identity matrix. Okay? So matrix powers are important. They're useful in theory and applications, and you're going to see that later on. Something else too, transpose, the transpose of a matrix. If you have a transpose of a matrix A, let's say the matrix A is an m by n matrix. Well, no, the matrix, yeah, matrix A is an m by n matrix. The transpose of a matrix A will be an n by m matrix. Okay, so, you know, how does this work? Well, let's take a look at example 8. You have a matrix A given by first row A and B, second row C and D. Transpose means the first row of matrix A becomes the first column of the transpose. And so A times B, which is the first row of matrix A, is going to be the first column of A transpose. Similarly, the second row of the matrix A, C and D, that row is going to be the second column of A transpose. Okay, let's look at the matrix B here. Matrix B, you have 3 rows. When you take the transpose of B, the 3 rows become the 3 columns. So the matrix B is a 3 by 2 matrix. The matrix B transpose is a 2 by 3 matrix. Okay, and these are transposes. Are there any questions on transposes? They're going to come up too. They're going to be important. Okay, and then finally, if there are no questions, a few more things. Okay, theorem 3, if you have matrices A and B, okay, then you have the following 4 rules that hold for matrices. So for instance, if you transpose a transpose, that's going to give the matrix A back. That makes sense. And it would probably make intuitive sense that A plus B transpose would be A transpose plus B transpose. But the last 2 rules are perhaps not quite as intuitive, particularly rule D. If you take A times the matrix product A times B and transpose it, it's going to equal B transpose times A transpose. But you're going to have a homework exercise that deals with you'll practice this with matrices, and you'll see that the transpose of a product of matrices equals the product of the transposes in reverse order. Okay. Are there any questions on that? All right, well, finally, they have always as always at the end of every section in the book, they usually have a numerical note. And they comment that the definition of the matrix A times B lends itself well to parallel processing on a computer. The columns of B are assigned individually in groups to different processors, which independently and hence simultaneously compute the corresponding columns of A times B. How many have done parallel processing on, has anybody ever done that with using different processors? I mean, I know some of you are in computer science. Wait, Benjamin's, and you have more expertise than I do on this, likely. But Benjamin says compute shaders on GPU. What's that mean, Benjamin? I'm not sure what that means. Does anybody have? Okay, Benjamin says running physics programs on graphics hardware, which is highly parallel. Okay, okay. So, and I can tell you that you're going to learn that we're going to need matrix multiplication to do animation. You're going to learn, let me see here, it comes up later on in chapter 2, section 2.7. You're going to have applications to computer graphics, and that's going to involve matrix multiplication. So, all right, thank you, Benjamin, for that comment. Are there any other questions on this? Okay, let me stop the recording.